Alright, this is the Quantum Physics Chapter 27 video, and I don't know how many parts it's going to take, but I'll stop the video if it gets too long and split it into parts if I have to. Right, so you should have your student notes that look like this to start with quantum physics, and I'm kind of going to go through a little bit of a history of it as well, in a sense. It's kind of the best way to see what happens and when it happened and how things kind of got pieced together. So, first looking at the discovery of the electron, we have what's called the J.J. Thomson's cathode tube, which he has a tube that has a battery kind of hooked to it. And so you have the cathode side, and then you have the anode side, and you have a screen. And he filled this tube with electrodes and a small amount of gas, and then applied a voltage to it. And what they saw was a glow on this side. So they could see that these cathode rays traveled from one side across, and there was a glow. So they decided to put this tube kind of within a magnet. And what they noticed was the paths changed, and they had three different paths. The first path that went straight ahead, we see this as when the electric field is equal to the magnetic field, and so there's no electric field, there's no magnetic field, and nothing's being detected. Right. The fact that they saw the difference of paths means that you are looking and detecting a magnetic field, and it's causing, the electric field, and it's causing the particles inside this beam to deflect. So path A, which if we look, this is the positive plate. This is with a E field present and a upper positive plate, and so the rays deflect upwards. Path C, which is when the rays are deflecting downwards, is with only a B field present. And so when you have a B field present here, if we look at the equations for force, we have F equals the charge times V times B. And then since it's deflecting downwards and changing its path, we have the force, centripetal force, is equal to mass times V squared over R. And so if we look at equating these two, right, so Q VB equals M V squared over R. And then we also know from previous chapters that V equals E over B. What we're going to do is plug in E over V for the V's on both of these sides. So we have Q E over B times the B, and then E squared R B squared. And these B's cancel. And so you have Q E equals M E squared over R B squared. And of course we can cancel these. And then we're going to divide the mass over. And so we have Q over M equals E over B squared. I'm switching order just to have it match up with that. And so we have a charge over mass. And what this charge ends up being is the charge of electron. Okay, now at the time they didn't know this charge of electron, and they didn't know the mass of electron. So that's the mass of the electron. But all they knew is that this ends up equaling 1.76 times 10 to 11 coulombs per kilogram. This happened in like 1898 or 1899, and then about 9 to 10 years later, another guy named Millikan did another experiment. Where he took oil drops and he dropped them through a magnetic electrical field and had a telescope to watch it. And as these fell, he measured how fast they would fall, and in order to find the force on them. And so if we would think about this, as these oil drops are falling, they are going to have some charge on them that goes with this force. And so this is just the electrical force, it's QE, and then the gravitational force is pulling it down, that's mg. And so if we equate these, we get that the mass times gravity over the electric field, which they would know the electric field of this, is going to be equal to your charge. They did enough droplets in order to find that every droplet had the same number that it was a ratio of, or a multiple of, and that number ends up being this 1.602 times 10 to the negative 19 coulombs. And so that's how they found the charge of electron. And then once they had the charge of electron, they put it into the Thomson's charge to mass ratio and was able to calculate then the mass of an electron. And now I don't remember the date for this one, but it came after, I know that, and it's the black body radiation, which we're going to be doing an experiment later on. I waited till more of the astronomy chapter to do this experiment, since it's deals with black bodies, which deals a lot with the astronomy. But it's good to get a kind of bit of a introduction to it. So a black body itself is an opaque object that emits radiation. And a perfect black body absorbs all light and reflects none. So they just say this ball here is a black body. Any light that goes towards it, it takes in, and it's not going to give out any light at all in form of visible light or gamma rays or anything like that. It does give out thermal radiation. And so a high enough temperature, the black body will begin to glow, emitting visible wavelengths of light. And as the temperature of the black body begins to increase, the wavelengths that it emits will begin to decrease. So, for example, if this red light here that it will eventually emit when it starts to glow, it's 3000 kelvins. If it goes up to 6,000 kelvins, it now emits a lower wavelength, and there'll be more of a green. If it's right in between, it's 45 kelvins, it's going to emit an orange wavelength. And so what they found that is this wavelength is proportional times the temperature is equal to 2.9 times 10 to the negative 3 meters Kelvin. And so for the first example we have in this chapter, we are looking at two different ovens, and oven A has a wavelength, a maximum wavelength of 6 micrometers, and B, should just do it like this, has a maximum wavelength of 7 micrometers. We want to see which one is cooler, and we want to figure out the temperatures of each of these. So we can look at temperature A, and it's going to be the wavelength times the temperature is going to equal 2.9 times 10 to the negative 3. So this temperature is going to equal the 2.9 times 10 to the negative 3 over the wavelength. So for A, it'll be 2.9 times 10 to the negative 3 over 6 times 10 to the negative 6. And for B, it'll be 2.9 times 10 to the negative 3 over 7 times 10 to the negative 6. And so temperature A will come out to be 483.3 Kelvin, and temperature B will come out to be 414.3 Kelvin. So the cooler one has the longer wavelength, and as the wavelength decreases, the temperature had increased. Right. And then now what really gets into the quantum is when Planck came up with his quantum hypothesis. This was a theory that was able to reproduce the black body radiation graphs. Because before this, they couldn't figure out why what was happening would happen. And so this is the fact that energy of atoms is based on the frequency of an oscillation for the atoms in a molecule. And so the energy cannot be just any value. The smallest value is the quantum of energy. Basically, you can only have certain number of energy coming out of a atom. So think of it as like counting numbers. They're not actual counting numbers, but you can only have 1 unit of energy or 2 units of energy. You can't have a 1.5 unit of energy. But of course, the number for this has to be something a bit different than just 1 or 2. And so what he found is that the energy is equal to H times the frequency. And H is his constant, and in joules per second, it's 6.626 times 10 to the negative 34. If you are working with EVs, which I usually just switch things over to joules and seconds, but if you are working with EVs, it's 4.136 times 10 to the negative 15. And this is EV seconds. And so this is basically his quantum of energy. This is for a specific frequency. And then since we're dealing with atoms, any energy from this has to be some multiple of this basic energy. And so n being the quantum number, n times that hf is going to give this energy in specific discrete values. Right, so for example, if we are going to calculate the energy of a gamma ray photon with 6 times 10 to the 22 hertz. Right, so to do this, problem 2, the frequency is 6 times 10 to the 22. H is 6.626 times 10 to the 34. And so this basic energy is going to be equal to H times the frequency, which is equal to 3.98 times 10 to the negative 11. And so this is the basic energy emitted for a gamma ray photon with this frequency. Now, if we were dealing with a quantum number that is not basically n equals 1, then, and we'll get more into the quantum numbers here soon, for instance, n equals 2, then it would just be double this, so n equals 3 would be triple this. It's always going to be in some factor or some multiple of this number for that particular frequency. And so what we end up getting into is a couple of theories of lights. This is one that deals with photons and the photon theory of light. Photon itself is that a light is being emitted by molecular vibrations contained in quantized amount of energy. And the amount of energy decreased in the molecule must also be quantized and be the same amount. And so for this energy is going to be equal to n minus 1 times HF, which is that energy packet. And again, this is light being emitted by molecular vibrations. I don't think I can draw on this. Okay, I can. And this is what's being decreased in the molecule. Okay, whereas up above the E times HF was the actual photon. This is the energy within the molecule. Okay, so if we expand this, we get, NHF minus the HF. Okay, and this is going to be what's being eliminated, or the energy of the photon being eliminated. And this again is the energy of the molecule. Alright, so we have what's called the photoelectric effect, which we'll be doing a lab on this. So this is kind of really important to look at. And it's going to be dealing with these photons. You have a light source that's coming down and it's going to strike a metal. So these purple lines are the light. This is some photocell, and this is some metal plate here, and you have it hooked up to a circuit. When the light shines onto the metal, it will cause metal electrons to eject off the metal and basically into this circuit. And so now you're going to actually see a current go through. And it's going to be basically caused by the light causing electrons to jump off the metal. Oops. I want the picture up. Okay. So we have what's called the Wook function, and this is the minimum amount of energy for a single electron to be emitted from the metal plate. So basically, if this light source that's coming out, it has to have E equals H times some frequency of that light. And this E is not high enough for the what's called the Wook function of this metal, it won't emit an electron. And if this E does reach that amount and is greater than that Wook function, then the electrons will be emitted and move through this circuit. Right, so now what has to basically think about like this: when you have an electron that's being emitted, it's going to then have to have energy to keep moving forward. So if you reach that amount, it's going to emit the electron, but then the electron has no energy after that. And so if it's greater than, what's going to happen is that electron will use this energy to be emitted, and then the electron will contain this energy. And so what the Wook function is the least, the maximum energy, or the energy for the least tightest bound electrons to be emitted. If you have more tighter bound electrons, it's going to require more energies for them to be released. And because of that, it's going to end up, they're going to end up having a lower kinetic energy because it's requiring more. Right, so let's look at this next example. I don't know why my thing does that. Jumps up. And I'll erase this. Alright, so we want to find the lowest frequency of light that can cause the release of electrons from a metal that has a Wook function of 2.8 EVs. Alright, so we can use this equation, HF equals KE max plus the Wook function. But they want the lowest, and so the lowest is going to be when your KE max is equal to 0. Right? And so in this case, your HF is going to equal your Wook function. And we want to find the frequency, so we're going to take the frequency is the Wook function over the H. Right now we're dealing with EVs, 2.8 EVs. In this case, we can just use H as 4.136 times 10 to the negative 15 EVs per second, or EV seconds. And so the EVs will cancel and we have hertz, which is what we want. We want frequency. And so if we put this in a calculator, we get 6.77 times 10 to the 14 hertz. And this is going to be the lowest frequency to get an electron to be emitted from this metal. Right, so we end up with two different theories now when it comes to light. Photon is one theory, and when this is dealing with discrete energy. Wave theory is another one, which we had looked at in chapter 24, dealing with light acting as waves and interfering like waves work. I don't know what that is. Okay. So an increase in the intensity of light means more photons are impacting the metal, resulting in more electrons being emitted. Wave theory agrees that the number of electrons emitted will increase. The max kinetic energy of electrons does not change if the intensity increases. And wave theory, unfortunately, will predict that the max kinetic energy will change. And so this is one where these two theories kind of differ in how light works. And then the max kinetic energy of electrons does change if the frequency changes. Wave theory predicts that the max kinetic energy does not change if the frequency does. So this is another one that has a difference in what is happening compared to what that theory would predict. And then if the frequency is less than the threshold frequency to emit electrons, no electrons will be emitted. And this is another one that would be different if we just thought of light as a wave. All four of these all work under the photon theory of light. But there are other things that are taken into account that even the photon doesn't seem to work, and so that's why there ends up being two theories here, or two conflicting theories. And so the main experiment is this photon electric effect that agrees with this photon theory of light. Let's see what the time is on this. Okay. Let me see how much we have here. Okay, I'm going to stop the video here, and the next video will pick up on the Compton effect, and we'll keep going through these. I don't want these videos getting too long. Alright, I'll see you in the second video.